Thanks.
Thank you. So yeah, thanks to everyone for coming along to listen today. My name's Molly. I'm in the third year of my PhD at the University of Leeds, based between the School of Civil Engineering and Earth and Environment. So my PhD project as a whole is focusing on surface water flooding in future climates. And the work I'm going to present to you today is specifically focused on the impact of the temporal distribution of rainfall on pluvial flood risk in an urban catchment in Leeds. So in terms of motivation, the motivation for this work is the knowledge of the risk already posed by surface water flooding in the UK and the prospect of this risk growing ever bigger in the future due to the combination of urbanisation and the intensification of rainfall due to climate change. So whilst there's been quite a lot of development in the tools to model urban flood risk in recent years, it seems that there's still quite a knowledge gap around the influence of the temporal structure of rainfall and how to incorporate this into modelling. So that's why I'm focusing on this. So I'm just going to give a brief overview of what I'm going to cover in the talk today. So I'm going to start by providing some background information on the current methods used for representing the temporal distribution of rainfall in flood modelling in the UK. And then I'm going to give an outline of some more recent research, which suggests that these methods are misrepresenting the temporal structure of real storm events. I'm then going to start to talk about my research, in which I assess flood model sensitivity to the rainfall temporal distribution. And using that, hopefully, I'm going to provide some evidence that this misrepresentation of storm temporal profiles does influence the resulting flood risk, and that this is something that the flood modelling community should maybe be interested in. Okay, so just a bit of background information to start with. As I've mentioned, the focus of this work is on the temporal distribution of rainfall within events. And to be clear, by this, I mean whether the heaviest rainfall within a storm event is concentrated at the start, towards the middle, or at the end of the event. So the distribution of rainfall is represented graphically using a hydrograph, which plots the rainfall intensity over the time period of the event. And you can see some examples of this kind of thing on the slide. And so in the UK, the industry standard approach to representing a rainfall event is to use one of two hydrographs defined in the Flood Estimation Handbook, or the FEH for short. So these are both shown on the plot here. As you can see, they are both symmetrical with a single peak in intensity and a kind of gradual build-up and decay either side of that peak. There's a bit of a variation between the two profiles. So the summer profile peaks more steeply and reaches a higher peak in intensity. However, like on the whole, they're kind of roughly the same shape. As I've mentioned, use of these profiles is really widespread in the UK. It's kind of what everyone uses. However, the evidence to support their physical basis in reality is actually really quite limited. So the profiles were first derived back in 1975. They were derived from a limited data set of just over 100 rainfall events. All of these events were of 24-hour duration. And yeah, they happened like 50, 60 years ago now. And there's been no updates or refinements to these profiles ever since. So this is where I'm going to mention some recent research done at Newcastle University by Roberto Villalobos Herrera. So the group in Newcastle have collected a very large collection of UK extreme rainfall events of all different durations, and they've used these to identify the most common patterns in temporal distribution, specifically using a k-means clustering algorithm. And the results they've produced from that show something quite different to what we see in the FEH profile. So they've done this analysis kind of broken down by duration bin of event. And the one I've shown here on the screen is for roughly 2 to 7 hour events. So you can see in the profile, for this duration bin, they've produced 15 different profiles, which represent the variety. And you can see that these are grouped according to whether they are front-loaded. So this is the F2 and F1 categories, centered or back-loaded, including B1 and B2. So this range of profile types doesn't actually occur they don't all occur with the same regularity. So in short duration storms, the centrally peaked storms, such as the FEH profile, are actually quite rare. So less than a quarter of storms are centrally peaked. And at short durations, the front-loaded profiles, so F2 and F1, are more common, and the back-loaded profiles of B1 and B2 are much less common. So this work has clearly established that the FEH design profile does not well represent the variety of temporal structures in rainfall events seen in the real world. However, evidence is still needed in order to establish whether this actually matters for flooding. So if we have multiple rainfall events with the same volume, but distributed over time differently, will we see differences in the resulting flood extent and severity? So that's essentially the question that I'm tackling in this research, which I'm about to present. So just going to start with a flow chart, which represents a simplified explanation of the usual flood modelling workflow. So you take a rainfall volume, use the FEH hyetograph to distribute this over time, feed this hyetograph into your flood model, alongside a load of other things, of course, and out comes an estimation of the resulting flood risk. So I'm going to take the same process, but instead of using that FEH hyetograph, I'm instead testing a variety of different hyetographs using a constant rainfall volume and the same hydraulic model each time, and observing whether we see any differences in the outputs, for instance, in the spatial extent, the depth, the velocity of flooding, which I'm then able to compare in order to establish whether the temporal profile is affecting the results. Or I guess the alternative outcome would be that we would see that really it's just the total event volume that is important, and the distribution over time doesn't really matter. So I'm just at this point going to give a few details on the model which I'm using in this sensitivity testing. So it's a rain on grid model ran in HECRAS using the 2D unsteady diffusion wave equation set. It's based on land cover and terrain data, both at 1 meter resolution, and it's ran for 12 hours. So I'm using a 6-hour duration rainfall event, but run for 12 hours with a time step of 1 minute. I'm going to talk in more detail in a second about the rainfall conditions, but I just wanted to highlight at this point that the model doesn't represent losses due to infiltration and natural drainage processes, nor to urban drainage systems. And so rainfall profiles need to have had losses removed before they're input into the model. The model is covering the Lyndyke catchment, which is to the east of Leeds. So it includes 2 urban areas in Kippax and Garforth, which you can maybe just about make out at the top of the catchment. It's also got some wetlands in the bottom area, and then it finally drains into the air. So the catchment is a bit of a known local flooding hotspot. It's had several incidences of fluvial flooding in recent years, which is obviously unfortunate for them, but means that it's quite a good case study for us. Okay, so that's the flood model. And I'm now just going to say a little bit more about the hyetograph variations which I've used in the model sensitivity testing. So the first thing I wanted to test was the impact of making idealized variations to the FEH design profile. So as I showed earlier, the FEH design profile has a single symmetrical peak, which you can see on the slide now. And we've basically developed an approach for allowing this peak to be shifted either forwards or backwards in time. Using this, we've created 8 versions of this profile, but with the peak shifted towards either the front of the event, as you can see in blue, or towards the end of the event, as you can see in the red colours. In all cases, the total event volume is based on a 6-hour, 100-year return period event, and the total event volume and maximum peak intensity are conserved, so stay the same between all of the profiles. However, as I mentioned earlier, rainfall profiles need to have had their losses removed before entering them into the HEC-RAS model. And so I've done this for these profiles using RefH2, so the revitalised flood hydrograph model, and assuming average summertime antecedent conditions. So the plot on the right now shows the profiles after the loss removal. So whilst the profiles continue to have the same total event volume, you can see that there's now not the same consistency in peak intensity. The reduction in intensity is much greater in the front-loaded profiles, which is likely because when the peak occurs earlier in the event, the catchment is still drier and it's thus able to absorb up more of the peak. Whereas if the peak doesn't occur until later, when the ground is already more saturated, then the catchment has less ability to attenuate this peak. Okay, so that is our first set of profiles. These have all been fed through the model, as we discussed earlier, and a load of results have been generated, which I'll just discuss some of now. So the plot on the far left shows the total maximum flooded area associated with each of these 9 profiles. So we've got the centrally peaked profile in grey, and then we've got the most front-loaded profiles in blue and the most back-loaded profiles in red. So this shows quite a clear pattern, with the flooded area progressively increasing as the event becomes loaded. The biggest change from the centrally peaked profile is from the most front-loaded profile on the far left. And this profile has also got an almost 10% smaller flooded area than the most backloaded profile on the far right. So it's about a 10% range between the two extremes. Also plotting the relationship between the minute of the peak intensity and the total flooded area, we can see that there's a strong correlation between those two things. I've also produced some flow hydrographs and looked at the timing of the peak flow across several cross sections in the catchment. The locations of these are marked on the map, and the plots you see on the left-hand side are moving progressively downstream from Kippaxbeck to Lindyke at the bottom. So this shows that the flood peak arrives later and peaks higher in the backloaded profiles, which are again in red, especially further upstream. So the biggest differences are shown for this Kippaxbeck profile. At Kippaxbeck, the most backloaded profile peaks, has a peak which arrives 107 minutes later than the most front-loaded profile, and it also peaks 15% higher. So this work kind of suggests that this model is sensitive to the temporal structure of the rainfall input, with late peaking profiles leading to more extensive and perhaps additionally more severe flooding. So this in itself is interesting and informative about the model's sensitivity. However, these profiles are idealized, and similarly to the FEH profile upon which they're based, they're probably quite unrepresentative of real rainfall events. Therefore, the next stage of the work was to investigate whether changes in the flood extent and severity were also found when driving the flood model with hyetographs based on more realistic events. So using the summary profiles derived from the observed rainfall events, which I mentioned earlier. So just to recap, I showed earlier that for a 6-hour duration event, there's 15 profiles. These are derived from analysis of observed extremes. And I've constructed a version of each of these 15 profiles for this catchment. So similarly to the idealized profiles, the total event volume is based on a 6-hour, 100-year return period event in the Lindyke catchment. The losses have been again removed from the events using RefH2. And in this figure, the 15 profiles plus the FEH profile in the top left are plotted and are shown both pre and post loss removal. So as you can hopefully see, there's some considerable variation in these profiles, including both in the timing of the peak and also the magnitude of the peak intensity. So yeah, taken this second set of profiles and fed them through our model again and got some results. I've again shown that the total flooded area for each profile, I've shown that in this plot. So we've got the most front-loaded profiles on the left in blue and the most back-loaded profiles in the right in red. And in this case, we're comparing against the FEH single peaked profile, which is in black. So again, this kind of considerable variation with the most backloaded profile associated with 8% more flooded area than the FEH single peak profile and 17% more flooded area than the early peaking profile, which is associated with the smallest flooded area, which is the second blue line to the left. So that's the range in total flooded area that we're getting. So it's also maybe important to point out that the profiles behind these results do also have quite large accompanying variations in peak intensity, as well as in the timing of the peak, and that this is also probably directly linked to the variations we're seeing in the flooded area. So if we plot the same data but ordered by the magnitude of the peak instead of the timing of the peak, then we can see quite a clear trend linking the peak precipitation intensity with the extent of the flooded area. So it's probably a combination of the two factors. So just looking at the timing of the peak flow across the same cross sections as we looked at before, can see a similar kind of pattern. So namely, the flood peak arrives later and in some cases peaks higher in backloaded profiles than in the front-loaded profiles, and that's particularly apparent in this Kipak spec upstream location. So just to finish, I wanted to try and put these results into a bit of context. So in this work, I've been focusing on varying the hydrograph profile and looking at the impact this has on the flooding output. But a more common focus is on the impact of changes to the rainfall volume, for instance, to account for the effect of climate change. So to offer a comparison of how relevant the changes I've shown here are, I also tested the impact of using the FEH hydrograph, but upscaling the volume of the 6-hour 100-year return period event for Lynn Dyke. It's not super easy to see on this plot just because of the shape of the profile, but I produced versions of the event with an extra 5, 10, 20, and 30% of volume added. And again, ran it through the model and plotted the total flooded area associated with each of these profiles. And from this, we can see that the changes in the flooded area we saw from shifting the peak are in many cases equivalent to the impact of increasing the total event volume. So that's just basically a bit of a comparison, I guess, to suggest that if scaling the event volume is seen to be important, which it often is, then accounting for the event temporal profiles is something that which should maybe also be considered. So to summarize, the temporal distribution is currently widely represented using a single peaked symmetrical profile in flood modelling. Recent research, however, indicates that this profile misrepresents the true range of rainfall temporal profiles encountered in nature. I've conducted some research into the extent to which this simplification of the profile actually matters for flood modelling. So into whether flood models are sensitive to the rainfall temporal pattern. I found that experiments with idealized profiles indicate that shifting the timing of the peak does influence the flood extent and severity, and that simplifying the variety of storm profiles found in reality into a single simplified profile does risk either under or overestimating the flood risk associated with an event of a certain return period or volume. Yeah, just very much final thing. Future things I want to do with this work. The analysis I've presented here, I'm looking at changes to the flooding occurring at any point in my catchment, but quite a lot of that catchment's rural. So I'd also like to break down this analysis further to focus on changing impacts in urban areas specifically, which I've started doing a bit of, and it looks like the urban areas are perhaps slightly more affected by these changes. Also want to look at whether the results are generalizable to other catchments, and how catchment characteristics perhaps influence this sensitivity. And fully look at how will the impact of the profiles change in future climates. So will this have more of an impact in the future where we're seeing more intense summertime events occurring in generally drier conditions? And that's it. Thanks very much for listening.